So, hello everyone. It's 3 p.m. and 2 minutes, so we are ready to start our today's webinar. Here we are at Elmarco. Jirka Mashkarenec, our senior scientist in R&D department.
And next to me is Ivan Ponomarev as a manager of R&D department.
So this is today's topic is electrospinning applied in lithium-ion cell production, and I also want to mention then that in next months we're going to have other webinars which you can see on your screen. So next Elmarco Talks, so don't miss them. And let us introduce our today's speakers.
Our today's speaker is Professor Karl-Heinz Pettinger, and his colleague is Victoria Peterbauer. The both of them are from the University of Applied Science from Landshut, which is mainly focused on research concerning various storage technologies in the battery sector, as well as research into transformation process in the field of power to gas technology. Professor Pettinger is a distinguished figure in the fields of electrochemistry and energy storage. He became a professor for electrical energy storage at Landshut University and led the Technology Transfer Center at the same institution. His colleague, Victoria Peterbauer, holds a bachelor degree from the University of Applied Science in Wales, and her academic journey continued with a master's degree in bio and environmental technology at the same institution.
So we will continue now with a short presentation about Elmarco, about our equipment, about our technology, and then we will give word to our guests. So our headquarters are located in Liberec. It's a city in Czech Republic, 100 kilometers to north from Prague. We have 20 years of experience in the market, a lot of patents related to technology, and not only technology, also recipes. We are a mid-sized company, and we are very known for our nanospider technology, which is based on free surface electrospinning. Main free surface electrospinning is based on fiber formation from the wire. In our main portfolio, we have laboratory equipment. It's left-hand side corner. Then right side upper corner, it's our NS pilot or laboratory machine as well. It's a 0.5 meter wide. And then both these machines gives you an opportunity for research and development work, which can be easily scaled up to our production machine, 1.6 meter wide, 1 meter wide. And we also working now on a new technology which calls Infinity Line. You may know that nanofiber has could be used in many applications, like air filtration. It's already adopted quite well. Liquid filtration, medicine, peripheral acoustics. But today we will be mainly focused on energy segment of applications, battery separators, battery electrodes, fuel cells, and this is very, very interesting and hot topic nowadays. I think we all understand and all know this. So now I would like to give a word to our today's guests. Again, as Jirka mentioned, Professor Karl-Heinz Pettinger and Victoria Peterbauer. So now it's your time, please.
Thank you very much for the nice introduction. And we are happy to be invited to give you a battery session about the use of nanofibers. We want to inform you about our project IntelliSpin. Click, Victoria. We have two partners in this project. One Click. The fourth partner is Landshut University with our nice tech center here on the countryside. So we are around about 20 to 25 scientists working on battery and energy storage and distribution. And the second partner is Technical University of Munich. So the project is driven by two professors, my colleague Rüdiger Daub from Technical University of Munich and me from Landshut University. And our colleagues working on this project are in Munich, Stefan Tratnik, who is really doing the development and control of algorithms for spinning by high-speed cameras and artificial intelligence. And here in Landshut, my colleagues Victoria Peterbauer and Jessica Kunzendorf are working on the battery basics, lamination development, electrospinning technology. So the two main competences in this project are in Landshut, lamination, battery production technology, and in Munich, the development of a regulating mechanism and the use of artificial intelligence. Victoria will show you in her presentation how clever this can be done and how good it is working. Next slide, please. I want to give you a short introduction into lithium ion cells, just some basics why we are electrospinning and laminating. Next slide, please. So in a lithium ion cell, we have two electrodes, one anode, one cathode, and in the middle is a separator. And there are two interfaces which are really important for the working and the aging of the cell. The first one is the anode separator interface, and the second one is the cathode separator interface. And the more stable those interfaces are, the more enhanced longevity the cell will have. Next, click please. No, the one too much.
Okay.
So the trick is to fix durable interfaces together. And we have one very important interface on the anode, this is the so-called SEI, solid electrolyte interface, which is in, let me say, 90% of all cases, the reason for early aging of lithium ion cells. The better controlled this interface is, the more long life the cell will have. Next slide, please. So if we are looking to the real electrodes, we have on the top side a schematic of the cathode, down the anode, graphite, and the separators in the middle. And the surfaces are not plain and smooth. And if we bring them together, laminate them together, there's no gap between separator and the anodes. And the gaps are really lethal and are reason for emerging SEIs and bad interfaces. Next click, please. So it consists mainly of a polymeric layer, and the formation and maintenance is really a high quality aspect of the cell. Next click, please. And on the right-hand side, we have now a real SEM photograph of a cathode, it's a cross section, and a separator and an anode. And now you see how unplane the surfaces are. And if we laminate them together and fix them together, then we stabilize the interfaces and bring the components together. Next slide, please. So this was the aspect of the interface, to fix them and to create longevity. The second aspect is the assembly of the cell. I have here a video of a cell assembly, a prismatic cell, which is being wound. And this video is really in slow motion. The actually targeted speed in battery industry is 30 meters per minute, not the slow motion one, it's 20 times more. And you can imagine if we are going for a machine with anode, cathode and separator with 30 meters per minute, then the electrodes are hardly to be fixed. And if we laminate them to the separator, then they are fixed and we can reach those high throughput in high-speed assembly. Next slide, please. How is it done? It is done in so-called lamination machines. one click, we feed the electrode and the separator together, fix them, and then in the preheating zone number 3, next click please, they are preheated, and with the roller presses number 5, they are pressed together and fixed together. Those lamination machines are standard in battery production. Not all manufacturers use them, but if we want to reach really high assembly speed, 30 meters per minute, then we require those lamination technologies. Well, this sounds easy, but why are we using now nanofibers? We could easily coat it with a glue, anything, and glue electrodes and separators together. So if we would spray a film to the electrode surface, then we would have a film which is blocking the ion flux, remember the first chart, between anode and cathode. And the trick now, if we apply a non-woven, next slide please, Victoria, then we apply a small spinning interface, and 99% of the surface for the separator remain open, and only 1 or 0.5% are blocked. But this little amount of glue is sufficient to fix the interfaces and to enable the high production speeds. So we could also spray like a lacquer over it, but then we will block all the interface. And this electrospinning technology enables to keep high speed assembly and also high charge and discharge rates. Thank you very much. This was my short introduction why we are using electrospinning in high-speed battery assembly. And now, Victoria, I hand over to you to give the details to the auditory.
Thank you very much, Mr. Pettinger, for the introduction. Dear ladies and gentlemen, I will now give you a brief project introduction. So now we go deeper into the project IntelliSpin. First of all, I will start with the motivation and the project goal. The motivation is to laminate water-based electrodes and polyolefin separators. And this should be done by using the electrospinning technology, because this technology enables the application of layers of the lowest mass loading, as Mr. Pettinger already said. The objectives are also a self-controlled electrospinning technology for coating separators or electrodes. Just one thing for the Elmarco hosts, could you please mute yourself because I hear myself? Okay, thank you. So this also, but this is done in the Technical University in Munich. And then subsequently, the lithium ion cells are to be laminated using coated separators, so electrospun separators. And this then should also be used in the industry. So the left part of this slide, the electrospinning part, it was already explained, so I will go in no further detail into that. I will start with the right side of the slide with the possible process routes. So there are 2 routes. The first route, so that what we chose, is the electrospinning route. So you have a cheap commodity separator, then the electrospinning, and then you can also laminate it and stack it afterwards. And the process B is the more expensive route, because you can also afford beforehand laminable separators, but as I've already mentioned, they are more expensive, and then they can be laminated and stacked. So what we will look into it in the further tests and results is how good do the laminated cells perform, and also how good do they perform compared to the laminable separators. Exactly. So, but first of all, I want to go into the chronological approach to the project. What do I mean by that? If you want to laminate and afterwards build a lithium ion cell, you have to do various steps. So please follow me by finding the perfect separator you want to use. In our case, we chose the PE-wet separator by the company Brückner. It's a PE-wet separator, so it can't be can't stand very high temperatures. You can see that on the right side on the diagram, because what we did is we laminated the separator at different temperatures and contact pressures, and then we find out the possible temperature and contact pressure range. We did that via a Gurley measurement, and then we measured the Gurley time. And at 20 degrees and 0 pressure, the time is around 100 seconds. And so we looked for results that were close to that. And we can see that we are in the range of 100 degrees and around, I would say, 0 to 20 kilogram. And with that temperature range, we searched for a polymer that's like meltable, we could say, in that range, and we found the FPO 3850 from the company 3M. And then we chose the 60 degrees and the 80 degrees. So we didn't took the 100 degrees range, because that's only working at 0 kilogram contact pressure, and we still want to apply at least a little bit contact pressure. And we can see here that at 60 degrees Celsius, we are close to the 100 seconds, the Gurley measuring time. And we definitely took this for further tests. And on the right side of this slide, we can see a SEM image of the laminated separator, but it's 80 degrees and 10 kilogram contact pressure, just to get an image how this may look. So, and then we laminated the Electrospin separator, the PE-wet separator coated with Electrospin polymer FPO 3850. And then we did the adhesive tension measurement test. And we can see here that the applied force, so how much force it took to separate the separator from the cathode or the anode again. And in the table on the left side, we can see the average force. It's for the anode 16.9 Newton per meter, and for the cathode it's 32.7 Newton per meter. And in the literature, it said that we need at least a force of 6 Newton per meter. So we definitely reach this value, or better to say, we have definitely enough force, so definitely enough compound, definitely good enough compound of separator and anode. So the next step we did is to build cells, of course. That's what we wanted to do at the very beginning. So we have the separator PE-wet from the Brückner company, then the polymer FPO 3850. The PE-wet separator was electrospun on both sides, roll to roll, in the NS lab machine. And then the bicells were built. A bicell consists of 2 cathodes, 2 separators, and the anode in between. And for the cells we used, we needed 6 bicells to have a 1 ampere stack, because we wanted to get close or closer to the industry. Those cells were filled with 6 milliliter electrolyte, and afterwards we started the formation, so the charging and discharging cycles and the electrochemical tests. And that brings me to the next part of this agenda already, the presentation of the project results. So here we can see on the left side the C-rate test. The C-rate test is more or less a stress test, because also in our daily life we wanted fast charge and discharge rates, especially for the cars, for example. So that's something we also do in the laboratory. We take a closer look at how fast we can discharge our cells. So that's the most intensive C-rate or discharge test we have is the 5C. So we can say this cell was those cells were more or less discharged with 5 amps. And so one point here in violet or blue is always an average value of 3 fabricated cells. And the violet ones are the laminated cells and the blue ones are the non-laminated cells. So we can see clearly on the C-rate test on the left side that the violet points showing a higher discharge capacity than the blue ones. So that means that the violet, so the laminated cells are showing a lot better capacity. They run better than the non-laminated cells. The same is also at the long-term test. On the right side, long-term test means that the cells are charged and discharged in a, I would say, lower stress, but still, but it's still very close to the reality. So we can see here that the laminated stacks are showing a better discharge capacity than the non-laminated stacks, and that goes hand in hand with the C-rate test. The drop you can see in the blue line at the long-term test was a temperature drop in the laboratory and has nothing to do with the quality of the cells themselves. And if we take a closer look below the long-term test, there are some numbers. The nominal capacity I want to point out means the capacity the cells have theoretically compared to the capacity the cell still has after the long-term test, shows that the laminated cells are definitely closer to the capacity the cell has at the very beginning than the non-laminated cells. So this also means that the laminated cells may live longer or have in a longer discharge and discharging cycles, a good discharge and charge capacity. The next test we did was we also compared not only non-laminated and laminated, but also, I always say it's kind of pressed. It's the second line in the table. It's also the PE separator, but there is no spinning polymer, so it's not electrospun, but it's still laminated, but it's not really laminated because we don't have a laminated compound in the very end. So it's more or less pressed via the lamination process. But when the cell comes out from the laminator, the parts of the cell are still loose. And here the fourth line, it's a single cell, and the separator is intrinsically laminable separator. That's also the reason why we have other lamination parameters, because this is a completely different separator than we usually used for the other tests, and we also have a laminated compound in the very end. And this test should show us how good our the laminated cells compared to the pressed cells, the non-laminated cells, and to the laminated cells with intrinsically laminable separator. So let's take a look at it. We have again the C-rate test and the long-term test. So the stress test on the left side shows us clearly that the single cells, so with the intrinsically laminable separator, have the best discharge capacity, but the electrospun and laminated cells are the next best. So we definitely see it's still some room for improvement here, but we are definitely on the right path, because the just pressed and non-laminated cells are worse than the laminated cells. And the same picture also shows for the long-term test that yellow ones are the best ones. They have the highest capacity, and then the Electrospin, so the orange line, is the second best. And here it's the same as in the test before. We always have 3 cells, and then we took the average of it, and you can see here the average values in the diagrams. And now I will show you just some something what the Technical University of Munich does. Of course, it's not everything they do, because that would definitely expand the time too much. But just let's take a look at it. So they take a look at the area coverage. They are very into also the scanning electron microscopy and what you do with those pictures afterwards. So they calculate via a code, so via the computer, how much of those samples is covered with fibers. That happens via coloring those fibers with a different color, and the program then can calculate how much of the surface is covered with nanofibers. But there is a little bit of a problem if the fibers are lying on each other. So if the surface is covered all the fibers, and so there are like kind of shadows, then it's pretty hard for the program to calculate that correctly. But that's something my colleague at Technical University of Munich works on. And it's also that the high degree of variation of the SEM images is kind of a problem, because as you can see on the right part of this slide, is that the pictures, for us, we would say they're pretty good for a program. They are very different and pretty hard to calculate correctly. And this one is an analysis of the electrospinning process. Let's start here on the very left end of this slide. We have the position of jets in image. The image shows like 2 centimeters of the wire, of the spinning wire. So the one, this one, the sledge is going back and forth all the time, and the spinning jets. So the orange ones are the spinning jets going to, as we see it, to the right side, and the blue ones going to left side. But this picture is turned 90 degrees up. So the blue ones are spinning upwards, and the orange ones are spinning downwards and going then up again. But that's not important in this part, because they are going to the substrate anyways. And then after the time, so we have here cycle n. Cycle n means it's this time is until the sledge comes again. So start with the sledge phase. That means the sledge was just here and the wire is wet again. Then we have the spinning ramp up. That means that some spinning jets are forming and they start spinning. After that, we have the throughout spinning, or the throughput spinning. So throughput spinning means this is the part where most of the spinning and most of the polymer is going to the substrate. And then drying 1 and drying 2, and those phases we definitely want to avoid, because the wire could get clogged, or the sledge could get clogged, and then we have to stop the process, clean it, and start again. And then we have the next cycle. This says us how good the spinning process is working, and also gives us a clue how fast the sledge has to go back and forth, so that we don't come to drying 1 and drying 2. And also how many spinning jets do we get. And out of those pictures, but I don't have this here right now, but we can also see if there's like a part of the wire where no spinning jets are ever. That's also something we could see. So it's very interesting for the also for the understanding of this process. And it's the only way to imagine how good the polymer fibers are in the end, because the only way to get information about that is a SEM picture, but it takes very long. And so we also want the SEM pictures and this process, while looking at it like this, to get combined, so that we can have kind of results as soon as we look at the electrospinning process on its own, and do not always have to take SEM pictures. And some technical and economical benefits if we use electrospinning for lithium-ion cells. The technical advantage is something Mr. Pettinger already mentioned, is we have an easier handling, especially at stacking, and also if we look right to industry with the high speeds. We also have like improved electrochemical performance. We have a reduction of capacity losses. That's also something I showed you, and improvement of cycle stability. And next to that, we also have economic advantages. It's a simple and easy to use technology. As soon as we have a process or a combination of separator and polymer that's working well together, it also simplifies the stacking process, and it enables fast assembly speeds. And so it reduces the costs of the assembly process. So, and the summary and the outlook, I want to point out here the 1 ampere stacks, because they are close to the industry. And yeah, we did the formation, the serial test, and the long-term test. I showed you that. And here are again pointed out the first cycle of the long-term test and the 200th cycle of the long-term test. And we can see that after 200 cycles with charging and discharging with 1C, they still have like more than 94% of remaining capacity. So what we want to do in the next time is we want to build further cells with detailed variation of the substrate speeds, and further electrochemical investigations, of course, further SEM images to assess fiber quality, and the homogeneity investigation of the substrate coverage, because here there are still you can see some difference in the coverages, and the observation of the spinning process and the comparison of the SEM images with the spinning process. If you want to go into more detail about lithium-ion cells in combination with electrospinning, I can recommend you those 6 papers. They were written also here at University of Applied Sciences from some colleagues of mine, and of course Mr. Pettinger. Yeah, and that was mainly it from me. If you have any questions, please don't hesitate to ask.
Okay, but meanwhile, I will pick up the first question of the chat and answer it. An anonymous is asking, so if I understand correctly, you are e-spinning the FPO adhesive polymer directly onto the PE separator. Is there no issue of charge built up on the PE repelling the fiber deposition? How is it spun to both sides? So we did not obey any charge repelling the fibers from the PE because the membrane is a porous one, the separator, and the grounded plate is just behind the separator, and therefore the electrical field is so strong that we did not obey any repelling, maybe by electrostatic issues or something like this. The electrostatic forces of the high voltage, maybe 30, 40 kilovolt against the grounded plate beyond the separator, is strong enough to avoid this. And spinning on both sides will be done by 2 units, one top down and the other one spinning bottom up. It cannot be done in 1 unit together. It should be 2 units, and to our experience, it does not matter much whether we are spinning from the top or spinning from the bottom up. Hopefully Victoria can answer this a little bit better because she did both directions already.
Yeah, what we did here is we have the NS lab, and so we spun the first side roll to roll, and then we have to re-roll it, and then it again was spun, but this time on the other side in the NS lab machine. That's it. I also was a little bit scared if I don't like damage the fibers because it's so oft rolled and re-rolled. But actually, at the SEM pictures, you don't see any difference if it's from the first step, the first electrospinning or a second electrospinning. So there's no differences. But we also have to mention that this polymer is so sticky. It's so clogged together. You can really hear it when you re-roll it. That it's like a glue already, you can say. It's pretty tough to handle as soon as it's somewhere near a surface.
The next question from Sandra Martinez is a quite good one concerning this really low-cost separator we were using, because we used just a PE separator, the cheapest of the cheapest, to test the electrospinning technology. You can apply it to any other kind of more highly evaluated separator, free layer, anything like this. But with the PE separator, we didn't mention any decrease in the mechanical properties of the separator. And the improvement was the non-laminatable PE separator, the very cheap one, could be laminated with electrospinning. Some other mechanical properties have not been obeyed because the temperature was really room temperature. There was no shrinking, no closing of the pores. To my opinion, the separator was in the mechanical properties, which are interesting for the machinery people and the process people, have not been changed. The third question is if the single cell results are better than the laminated results, where are the benefits described by Professor Pettinger? Victoria, I think that you answered this.
Yeah, the single cells were also laminated, but with another separator. The separator used here was the PVDF with aluminium. And this one's intrinsically laminable, so we don't have to electrospin it. And this one was also like just a reference in how good are these cells running next to the laminated cells with electrospinning. So of course, the benefit that Mr. Pettinger described at the very beginning are valid here because they're both laminated. But I definitely have to mention that this separator used for the single cells is a lot more expensive than the PE wet separator and with electrospinning.
Victoria, the next question is one for you too. I want to ask about the thickness of lamination electrospun coating. How thick were the fibers? So the coverage was really little. It was 0.5 to maybe 1. I saw experiments with maximum 4%. But what was really the thickness of the fibers you applied, and which thickness would you recommend for this process?
Yeah, the thinner the fibers are, the better it is because of the coverage or better to say, the clogging of the pores. And the thickness of the fibers we had were around 250 to 700 nanometers. And yeah, the thickness of the coating itself, it's also about this range because we don't coat the whole surface, but just very little percentage of it, like 0.5 to 1%, something like that.
Thank you. And just one remark that the chat has not been open. Now it's open. And the last question in the chat is, did you get a chance to compare the separators coated with the E-spun nanofibers, your solution, to commercial references with ceramic coating, but with more conventionally coated PVDF adhesive layers? The reference slides 19 to 20 are ceramic coated. Therefore, we have to state that on the slides on 19 and 20 were done with a ceramic separator, which was coated afterwards by electrospinning to make it laminatable. And the other solution would be the sprayed or printed solution with a blocking of the electrodes. Victoria, do we have lab data about such commercially available solutions?
Maybe somewhere on the server, but right now not in my brain. So I don't know how far they are away from each other or how close they are. I can't answer that right now. I have to look it up because that was not that big part of my of the project.
We always compared the non-coated separator interface with the electrospun interface, and we saw that the C-weight capability remained the same, but we didn't do the vice versa experiment to use the completely coated and blocked separator. This would be one of the next steps to point out what's the difference of this. I give one issue with you. If you are using PVDF. PVDF is always sucking electrolyte and building a kind of a pseudo shield. And the more PVDF in the interface, the more electrolyte is bound, and the worse the energy density will be.
Karl-Heinz, there's another question. How it can be cheaper if you have an extra step in the process? Yeah, this means the comparison of intrinsically laminable separators and the electrospun laminable separators. Of course, we have an extra step in the process, but the PE wet separator, for example, is so cheap and such a lot cheaper than the intrinsically laminable separator that we have like such a lot of amount of money left we could use for the electrospinning machine. And we also calculated the cost of a square meter with the biggest electrospinning machine that's available, and we are within some sense, but the difference between the intrinsically laminable separator and the electrospun laminable separator are a lot bigger. So it's definitely worth it to use the cheap PE wet separator, for example, and then electrospin it and afterwards build cells, because the cells are definitely running a lot better than without electrospinning, if we just compare the PE wet separator. And it's also when we have in the process, in the industrial process already the lamination step, it's just one step more, but we are then completely flexible. We can laminate every separator we want to have, not only the intrinsically laminable separators, but also all the others, if we apply some nanofibers on the surface.
But in principle, we are free to apply electrospinning in the battery process in several steps. One we showed you was coating on the separator offline with our Elmarco technical machine. It can also be implemented in an inline process before the laminator, when the separator is derolled and going to the lamination. Or it's also possible to coat the electrodes with electrospinning and apply them, and either coated electrodes and coated separators can be stored offline in a stock under normal storing conditions for those materials. For cathodes, it should be relatively dry. Anodes, medium dry. Separators, keep them medium dry. But they can also be applied inline as inline modules and save one step of upwinding and dewinding in the process. So, to my opinion, if a fab or line is starting, I would recommend to apply it offline, because there's more variability in the process and you can keep several materials in stock. But if it's going to really production with high speed, then it should be implemented inline and never stop a running machine. Okay, there's one more. Next question. Do you do any work with e-spinning, the separation membrane, or electrodes themselves? Yes, this was what we were doing offline. Victoria showed the results of offline spinning of the separator, and we also did it with the electrodes. But honestly spoken, in this project, we preferred the separator, because I showed you the SEM cross sections. The surface of the separator is much, much smoother than the one of the electrodes, even if they are calendared. But in principle, we did it also with anodes and cathodes. The results are the same. The consumption of the polymer applied to the electrode is a little bit higher due to the morphology of the surface of the electrode, but both is possible. The next question is, have you tried to electrospin other adhesive polymer and compare it with the FTO? Victoria, please start.
Other adhesive polymers, not in this project, because we chose the PE wet separator, and it's pretty hard to find polymers that work in those low temperature ranges. Of course, if we would take a ceramic separator, we would have many, many more polymers we could choose from. But so in this case, we more or less have only the FPU 3850, and compare with FP with the FPO is not what we did in this project, because it was never in my mind to compare it with another technology of electrodes. What I wanted to show is how good the lithium ion cells work with the same electrodes, but with a different system of separator.
But we did also spinning with standard copolymer, with melting point round about 150, 160 degrees, but it can be spun only on separators that withstand this high temperature. And that's where we choose those ceramic separators, and we applied on then standard copolymers, maybe very crystalline, medium crystallinity, and low crystallinity of polymers. But as Victoria stated, the bottleneck is the thermal behavior of the separator, and also the melting temperature for lamination for the polymer. How does the homogeneity of the standalone nanofiber mats vary with set dimensional thickness, not of individual fibers? What's the thickness of a possible mat? I think this question is going into direction of solid state based batteries. Victoria, you can show a little bit our activities too in this field.
What we also did in this project is we tried to take a closer look at the substrate speed, so how fast we can spin the separator, and the results or the cells are still running pretty good, because what I just came into my mind, what I forgot to mention, is that the substrate speed for the separator for the cells here was 200 millimeter per minute, so pretty slow, I would say, to have like good and like kind of a lot fibers to make sure that the lamination is good working. And what some of my colleagues do, they also electrospin, but the electrode, especially the cathode, and do that for the solid state batteries. So they wanna have like a thick layer of it, so that they don't need another separator or something, and they can.
So may I continue with questions? I think we will just maybe two more questions. So one of the question from our side, it's I think it was in the chat as well, but any really big issues with the spinning onto separator? Did you face this with the deposition of nanofibers, or it was quite smooth?
The one thing we found out is that I'm just missing the English word. The water dissolved in the air. I think you know what I want to say.
Relative humidity, you mean?
Yeah,
Exactly, humidity. That's what I was searching for. Has to be lower than 30%, because otherwise this process isn't working as it should. So the fibers are very nice when the humidity is below 30, but as soon as it is above, then you have like the spider fibers, that's what we call it, when they're just anywhere and look anyhow, but not as they should.
Yeah, okay, great, thank you. So yeah, spider fibers also are called as loose fibers, and another wording for it is flying fibers. So a lot of different description for the same thing.
Yeah, I have a question also. Is using electrospinning in construction of lithium-ion cell, is it profitable? Is it economically justifiable?
Yeah, it definitely is if you wanna have lamination in your process, and lamination is definitely a good choice, because the lithium-ion cells run a lot better than without lamination. And if you want to have like different types of separators, not only the intrinsically laminable separators, then it's definitely a good choice to do so. So that's what our result is.
Yeah. And maybe one in the same sequence, the question related to this a bit. So current battery production, like industrial one, what is the approximate ratio between battery making, including lamination process and without lamination process? Could you just give us any ideas on this? Or it's always with lamination in industry?
Yeah, what, for example, the set folder does is also kind of a lamination because it's pressed with a lot of temperature. So it's not lamination as Mr. Pettinger showed us, but it's kind of it. So there are, of course, many producers, or at least some, maybe Karl-Heinz, you more know that into more detail, but they are using also lamination and also like kind of it.
Yeah, the problem is an easy one. We are working with high speed. The separator is very low weight and the electrodes are heavy weight, and you have to fix them together in the same speed so that they are really mounted within the tolerances of, let me say, 0.2, 0.1 millimeters, not more. And therefore you need any kind of adhesion, prefixing, anything. And if you're prefixing, you can directly fix the interfaces and produce high quality cells.
Okay, so in other words, if we talk about future, it will be related to lamination process anyway, otherwise you couldn't get a good quality.
I think most of the gigafabs go to lamination because otherwise they would never ever come to the throughput of gigawatt hours per year.
Okay. So I think we listened today, very interesting topic, very interesting talk from our guest, from Professor Pettinger and from Victoria Peterbauer. Thank you very much for your talks, for your time, for help with the moderation of discussion due to technical issues on our side. So if you have any other questions, please contact us, Elmarco, contact us via all possible channels of communication, email, etc., our social networks. So we are very pleased having you here today. Thank you to our audience that you spend this time with us, and see you hear you next time during our webinar.
So thank you very much for the invitation and have a nice afternoon.
Thank you. Have a good rest of the day. Bye-bye.
Bye. Thanks for having us.